Welcome to the Chemistry 209 Masterclass series. This series of lectures is intended to highlight the key concepts of introductory spectroscopy and structure. This lecture, Masterclass 11, discusses electronic spectroscopy. To this point in Chemistry 209, we have focused on molecular transitions that occur between rotational and/or vibrational energy levels associated with a single electronic state. It is, however, possible for molecules to undergo transitions to rho vibrational levels associated with a different electronic state. Electronic transitions are usually much higher in energy than vibrational and rotational transitions. Thus, electronic transitions typically occur in the visible or ultraviolet regions of the electromagnetic spectrum. Regardless of size, shape, or symmetry, every atom and molecule will have an oscillating electric dipole moment and will therefore have the potential to undergo electronic transition. We saw in Master Classes 3 and 4 that there are an infinite number of electronic states that converge to the ionization energy limit for atoms. The same is true for molecules. Fortunately, owing to the transition selection rules arising from conservation of momentum and symmetry arguments, only a small fraction of the infinite number of possible transitions are allowed. When considering electronic transitions in molecules, we must remember that within the Born-Oppenheimer approximation, electronic energies depend parametrically on the nuclear configuration. This results in electronic potential energy curves for diatomic molecules and hypergeometric potential energy surfaces for polyatomic species. As we will see, the relative form of the potential energy curves or surfaces has important bearing on the probability of electronic transition between the two surfaces. In Masterclass 5, we learned about molecular orbital theory and found that electronic configurations give rise to specific sets of quantum numbers, each of which can be summarized with a term symbol. For example, the ground state electronic configuration of molecular oxygen yields triplet sigma G minus, singlet delta G, and singlet sigma G plus terms, which have that energetic ordering based on Hund's rules. A potential energy curve diagram of molecular oxygen is shown on the left. We see that all three of these states are deeply bound by tens of thousands of wave number, and that the shapes of their potential energy curves are reminiscent of the Morse potential that we discussed in Masterclass 8. Since each potential energy well can support a number of vibrational levels, we find that electronic transitions between different states are accompanied by vibrational band structure. Furthermore, each vibrational level has associated with it a ladder of rotational energy levels. Owing to the large number of possible molecular electronic states, some shorthand rules for state labels has been developed. The ground electronic state is referred to as the X state. Excited states with the same multiplicity as the ground electronic state are labeled with capitalized Roman letters that progress alphabetically as energy increases. Excited states with multiplicities differing from that of the ground state multiplicity are labeled with lowercase Roman letters that progress alphabetically as energy increases. To determine transition probabilities or intensities, we must consider the transition dipole moment integral. If we ignore rotation and nuclear spin contributions, the Born-Oppenheimer approximation allows us to write the total wave function as a product of the electronic wave function and the nuclear vibrational wave function. Thus we find that the transition dipole moment integral has contributions from the electronic transition dipole moment and from the vibrational wave function overlap integral. The electronic transition dipole moment gives rise to the selection rules for the electronic transition. The vibrational wave function overlap integral describes the probability of a transition occurring between the two specified vibrational states. This is known as a Franck-Condon factor. The electronic transition selection rules for molecules look somewhat familiar to those that we found for atomic transitions. Here we find that the orbital angular momentum can change by 0 or plus or minus 1, and that transitions must occur between states with the same value of S and sigma. Notice that there is no delta V selection rule. Recall that nuclei are stationary on the electronic timescale within the Born-Oppenheimer approximation. So, when electronic transitions occur, the nuclei remain in fixed positions. On our potential energy curve diagram, we would represent such a transition with a vertical projection of the ground vibronic state onto the excited state wave function. The larger the overlap between these functions, the more intense the vertical transition. This, of course, is a graphical representation of the vibrational overlap integral. Given this idea of vibrational wave function overlap, we can envision two scenarios for electronic transitions. Either the two states exhibit similar chemical bonding, and are just offset energetically, or the two states exhibit different chemical bonding character and are offset both energetically and in terms of nuclear configuration. Assuming excitation from the V double prime equals 0 level in the electronic ground state, the first scenario results in optimal wave function overlap with the V prime equals 0 level in the excited state, and very poor wave function overlap with any other excited vibrational level. This results in a so-called short progression, since as V prime progresses to higher values, transition intensity decreases rapidly. The second scenario results in optimal overlap with a wave function where V prime does not equal 0, and significant wave function overlap occurs across a range of V prime values that are similar to the optimal value. In this case, a long progression is observed for a series of transitions between the V double prime equals 0 and the excited state V prime levels. By measuring a number of vibrational transitions associated with a range of V prime excited state levels, we are able to extrapolate the data or use an analytical model to determine excited state dissociation energy. In some cases, Franck-Condon overlap occurs with continuum wave functions just above the dissociation threshold. This facilitates direct measurement of dissociation energies. To determine excited state molecular geometries, it is necessary to resolve and analyze rotational level structure. Rho vibronic transitions are simply the change in electronic energy plus the change in vibrational energy plus the change in rotational energy, and transitions are subject to the combined selection rules. Note that for electronic transitions, it is common to observe a change in orbital angular momentum. In these cases, the regular delta J equals plus or minus 1 selection rule must be amended to delta J equals 0 plus or minus 1. Thus, Q branches may be observed in addition to the P and R rotational branches. For example, in the singlet pi to singlet sigma transition of aluminum hydride, delta lambda does not equal 0. As a result, a dense, closely spaced series of Q-type transitions are observed near the vibronic band origin. Note that the Q branch is degraded away from the band head. This is a direct result of the difference in rotational constants for the two states. If we employ the delta J equals 0 selection rule to our transition expression, we can write the analytical expression for the Q-type transitions shown here. It is now obvious that if the excited state rotational constant is smaller than the ground state rotational constant, the Q branch will begin at the band origin and extend to lower frequencies. This same condition results in an R branch bandhead. Alternatively, if the excited state rotational constant is larger than the ground state rotational constant, the Q branch starts at the band origin and extends to higher frequencies. This condition would also lead to a P branch bandhead. In Masterclass 8, we learned that bandheads always occur in the R branch for vibrational spectroscopy. This is a result of the increase in mean bond length as a function of vibrational quantum number, owing to the potential energy anharmonicity. The change in mean bond length upon electronic excitation can be very large, and it depends on the difference in chemical bonding character between the two electronic states. Recall that bandhead formation arises when the separation between rho vibronic transitions goes to 0. Thus, we can set the derivative of the R of J and P of J expressions with respect to J equal to 0 and determine the J value at which the bandhead occurs. This treatment is usually accurate to within 1 J value. In Masterclasses 2 and 3, we saw that atoms have an infinite number of quantum states that converge to the limit where n equals infinity. The same is true for molecules. This convergence limit is a precisely defined energy above which the electronic wave function is no longer confined to the Coulomb potential associated with the positively charged nuclei. In other words, the upper limit of electronic excitation energies is the ionization limit, or removal of the electron from the atom or molecule of interest. If we surpass this limit via excitation with light, the resulting photoionization process causes ejection of an electron from our atom or molecule. The process of photoionization is commonly used for spectroscopy, and it will be discussed in more detail in Masterclass 12. See you next time.